Welcome to another episode of Robo Papers. Super glad to have Stone Tao joining us today. So today we're doing something a little bit different. Instead of going through a specific paper, actually we're going through more like a long-term project, which Stone is leading. It's called ManiSkill, which is a simulation platform for robotic learning. So anyway, Stone, great to have you. Thanks for making the time. Maybe as a start, you can share a little bit about yourself, your personal background.
Yeah.
How do you end up doing ManiSkill, I guess?
Yeah. My name's Stone. I'm a rising third-year PhD at UC San Diego. I am currently advised by Professor Hao Su. Some people might know as for ImageNet fame. That's why he gets most citations of. But he also worked on a lot of other things like point and whatnot. My primary research interests are all things at the intersection of simulation and machine learning. So I don't work purely on simulation technology, and I also just don't work purely on algorithms. I think there's a lot of interest in combining these two in many ways that we don't expect to make things better. In terms of how I got started, it kind of goes way back to me competing in AI competitions. I used to compete in an AI programming competition called Battlecode for fun. It's run by a bunch of MIT students. It's designed for students to compete in. You write like a bot in Java. You write rule-based AI, not RL, but rule-based AI to like compete in a game they design every year. And it was pretty fun. That kind of was what spurred my interest in AI and some parts of, autonomous learning or like reinforcement learning initially. Did pretty well in the competition, retired from it because it took too much time. I did bomb like a couple midterms to compete in that. And so around the time when I stopped competing in that is when I started taking more AI courses at UCSD, one of which was my current advisor's course. Learned about computer vision, learned about robotics, learned about robot learning and reinforcement learning. And the only topic that hit home was reinforcement learning. Like this stuff was cool. It has a lot of potential, is very uncertain where it will go, whereas computer vision was getting more and more saturated. And so I applied to join Hao's lab as an undergrad, and coincidentally, the very first project I worked on at his lab was building simulation environments and doing RL testing in the first iteration of the ManiSkill project. There have been 3 so far, but the very first one was very focused on generalizable robot learning. So, training a robot model to control a bimanual mobile robot to kind of like move objects around or like open cabinets, open drawers. That was kind of like the first ManiSkill project.
And which year was this? You mentioned
so ManiSkill 1 was
like
around 2021. Yeah.
Can you talk about why you guys decided to like build your own simulator in the first place? Like as opposed to there were other simulators around then.
I think I can only hypothesize because I don't actually know the true reason. I was just an undergrad at the time. But you can look at some of the motivation for the original paper that ManiSkill 1 was built on, which is called Sapien. Sapien, I can't remember what it stands for. It stands for like simulated part simulation engine or something. It's like a custom physics engine that combines physics, at the time CPU physics, with our own custom Vulkan-based renderer. I remember some of the original motivations were we weren't super satisfied with existing renderers, and we couldn't do a lot of things flexibly. Like, I don't know, we wanted to render all kinds of things like albedo maps, normals, I don't know. That might have been one of the reasons. And then another reason is we wanted to build a system for doing generalizable robot learning. I think a lot of existing platforms are very like restricted. Like if you look at MetaWorld or like D4RL, it's really just like one task with some spatial randomization, but not geometry-based randomizations. I think concurrently Habitat was starting to be released from Meta, and they also started exploring geometry-based randomizations. So concurrently with us, we were kind of both exploring like, okay, we want to train robots to generalize over different geometries. Can we use simulation to do that? And the answer is partially yes. We didn't really do much sim to real on ManiSkill 1. We only started doing it more on ManiSkill 2 and 3. But it was part of our journey exploring the simulation space and like seeing like how can we improve on things. And so part of the design of the Sapien engine, which powers ManiSkill, which is based on physics and Vulkan, was designing software that's very amenable for supporting heterogeneous simulation. And what does that mean? That means like, each parallel environment or each environment can randomize geometry, randomize the articulated objects, articulations being like cabinets, fridges, things that can move with joints. And so that was kind of the big focus of that. I'm trying to tackle those kind of problems. A little bit niche at the time. Yeah, and then actually ManiSkill 1 had a competition associated with it. We did it in collaboration with some people from Sergey's lab, if I remember correctly, that run decently well. We had some support from Qualcomm. We tried to get people to submit online submissions to our competition. Worked out well, okay. I have my own opinions on robotics competition these days, but that was a really good kickstart to give us some motivation to keep doing the next iteration of the project.
What are your opinions on robotics competitions these days?
My personal recommendation is they are very, very hard to make popular.
Yeah.
Like I think we were both on a panel last year for the CPR competitions last year for robotics. Yes, the competitions are great research competitions. My main concern is they often don't get nearly enough submissions I would hope compared to other competitions that I've run actually, not for robotics, but for other things. You know, these competitions average like 5 to 10 teams. The biggest competitions I'm aware of is the one called RoboTwin. This is from China, which actually is also based on Sapien. They got at most maybe 80, 90 teams, which is very impressive, but that's not accounting for the fact that they spent some money on PR and advertising, which, you know, my lab is not going to bother doing. And so this is actually kind of reflected in ManiSkill3's competition where we ran one again, but we had even less teams. So that was complicated. And I suspect the reason is it's very hard to get good teams because, you know, the best people who are in the PhD program don't have a random 3-month block to allocate to doing a competition. That's what makes competition running very, very difficult. I do advocate for long running competitions, but like more short-term ones are 3 to 6 months. I've personally found it very hard to convince people to compete in. And oftentimes because of the short time frame, these competitions often yield submissions that are basically like, you know, fine-tuning PPO, fine-tuning the baseline, or making a very, very small addition that, you know, is not far different. And I'm vaguely aware that some competition organizers will make the baseline inherently weaker. Like they don't tune it that much just to encourage more submissions, to lower the barrier of entry, to at least, you know, beat the baseline. This is actually a design approach used by many AI competitions. Including some of you might know, I run a competition on the side for fun called Lux AI Challenge. It's a style of like programming AI bots for a new game that someone designs every year. I designed them with my co-founder. This series of competitions, like Battlecode, like Halite, which was run by 2 Sigma, very similar competitions, will actually purposely make the baseline super, super weak. And that way people can like tune in and modify it. And so in some sense, there's a lot of like conflicting parts with research world and competition design. So I've always found it hard. I'm very impressed that RoboTwin was able to get so many competitors, but you do need some bit of money and finding a way to find people to sign up.
Yeah, that makes sense.
Yeah.
Yeah.
So I have a lot of things actually to say about robotic competition. So we run one called twice now, IROS and then ICRA recently called Earth Rover Challenge. These are like real sidewalk robot, like basically we place in the real world, and then but our benchmark
you have it
is
ready.
Yeah. So we have these buggers running around in about like 10 cities around the world, and so this is truly in the wild kind of competition. And so I totally see all the pain points that you mentioned. Like, you know, it takes a lot of effort, and if you really want good teams, there are only just that many with a 3-month block to do something. But I totally see the challenge you mentioned.
I do think though, like in-person competitions are far easier to do in some sense. Like if you look at IEEE, they've been running like robot soccer and robot mouse competition, like a mouse maze, I forgot. You have a mouse robot solving a maze, and the goal is to do it as fast as possible or win the soccer game. Those have tons and tons of participation. Like maybe 20 to 100 universities across the globe are competing in those things, and they, you know, send people on flights to places to compete. I tried to figure out what was the secret that made those work, and honestly, I think it's because they're targeting undergrads, not graduate students. I don't recall seeing any graduate students at UCSD competing in them. It was mostly just undergrad student orgs that did it. And obviously, there's a lot of funding from IEEE to like market things and provide, you know, equipment actually to students to compete in these things.
And it is also valuable that it's every year, like it's a year.
Yeah,
like
that's
you
also
get a year,
thing.
not 3 months, right?
Yeah,
like, you know,
definitely for sure. But even then, like those RoboCup, those robot soccer competitions are actually not really designed for research. It's more like education in most sense. And
Well,
so
STEM,
I think
I guess.
educational kind of competitions are easier to design for competing
Yeah.
competitions in some sense.
makes sense.
At least in the realm of robotics, obviously. There's a little bit of tangent on robot competitions. I think, what was the original question? I guess it was about ManiSkill 1's.
Yeah, so you're saying ManiSkill3, you did another competition and then even less people. but
Yeah,
I guess
we had less
at
teams.
ManiSkill2, yeah.
I think we put most effort in ManiSkill. Actually, I think in terms of all the ManiSkill papers, ManiSkill 2 is the most popular currently. Like it has the most citations. Most people are still using it, although many people are now transitioning to ManiSkill 3 for its nice features. So Jiarian, the leader of ManiSkill 2, who recently started to become a professor in Shanghai, led the project, did a great job increasing the number of tasks, increasing lots of demonstration data sets for all those tasks. So you can do imitation learning or learning from demonstrations, a lot of interesting research that you can do, and then a lot of interesting papers did come out of that. Most of my algorithms research before I started doing simulation stuff was based on ManiSkill 2 as well. But the competition, again, was hard to get people to compete in. You know, even if there's a prize pool, it's hard to convince people. I cannot really tell you the exact reasons why, but these are my suspicions. And yeah, and a lot of the ManiSkill2's motivation is primarily around just fixing all the ManiSkill 1 issues, which is some usability issues. We actually improved the renderer speed a lot. I think at the time, ManiSkill 2 was actually still the fastest renderer. Like if you had a decent number of CPUs, like 128, with one GPU and 128 CPUs, we actually already had a form of tiled rendering or parallel rendering, where each parallel environment is being rendered simultaneously on a GPU very efficiently. And that was achieving like 3,000 to 4,000 FPS, which was beating, you know, all the other simulators. Like at the time, Isaac Gym was released too, and we are faster than them because they don't optimize for rendering speed. They only optimize for state simulation speed. So that was another big feature of ManiSkill 2, which is very fast visual RL. That's like a 10x on previous simulators, approximately. And that was some of the motivation for building that. Like we were building our simulation engine further, and we wanted benchmark to support that.
Yeah, maybe this is a good time. I don't know whether it's a good time to talk about it. Like what are the different dimensions that, you know, these users of this simulation engine would care about? So you mentioned a couple. You mentioned, you know, frame per second. You mentioned like state, you know, estimation parallelization. So what are things that? And I saw that you have a very good chart where you compare ManiSkill to a bunch of others on the site. I don't know whether that's a good place to show. But yeah.
You mean like our tech stack comparison?
Yeah. Well, let's...
Yeah, like
I can try.
You mentioned a couple of them, like large scale demonstration data, GPU parallelized simulation, things like that. And so if you can talk through each of them, like for those who are new to simulation,
yes,
like why do they matter? And, you know, yeah, I think it would be a
let me
good way
just
to
share
give the context.
The general tech stack of simulators. So this is what I usually share with people. This is obviously not complete because there's actually a lot of other simulators out there, but this is just kind of an example.
Yep.
Every single like suite, like at the very top level, people have heard of like Isaac Lab. That's the one that's being advertised by NVIDIA. Very powerful, very good for locomotion and other things. There's another project called Omni Gibson from Stanford and the Tepe's group. There's other ones you guys might have heard of like RoboSuite, RoboCasa, Habitat, Meta's Habitat Simulator, and Allen AI's Thor Simulator. There's many. At the very top layer is what we like to define as tasks and APIs. And also, I want to give credit. This is originally designed by my lab mate, Tungjo Mu. Tungjo just graduated. But yeah, at the very top level, we have tasks and APIs. What is that top level for? That's basically just to say that you don't have to touch any of the C++ code that's done for simulation or any of the low-level Python code that's being written for doing rendering and simulation. You get a very simple interface that actually all of these libraries adopt called Gymnasium, which is like a generic interface for interacting with environments. That you can take actions in an environment and you get observations back and potentially other data. And so that's in like the task part, like ManiSkill, Isaac Lab, Omni Gibson, and other benchmarks or frameworks will have a bunch of pre-built environments that you can just run out of the box. They've already been designed for you. For example, we have a cube picking one, we have humanoid manipulation ones, locomotion, random other kinds of environments. And the APIs part of it is, okay, we want to abstract away a lot of the low-level code that's happening in Sapien, which is the engine powering ManiSkill, or Isaac's the engine powering Isaac Lab, or the Omniverse tools, which are being used to power multiple other projects. And because we don't want people to deal with like tensor indexing, we don't want them to deal with memory allocation. There's a lot of messy things. And so we give them easy APIs to use, right? Every single benchmark has to think about API design. So these include APIs for like how to add objects into an environment, right? If I want to build my own environment, let's say I want to create an environment where I have a desktop table and a computer on it, and a robot to open the computer. I have code and APIs designed to add objects into the scene, add lighting, add cameras to the scene, add different kinds of sensors, change the simulation parameters, such as, you know, you can simulate it faster, slower, or at different resolutions of accuracy. And also define things like reward functions, which are very useful for reinforcement learning, or maybe even modify the observation information for state-based reinforcement learning. And so that's kind of like task and APIs level. I work primarily at that layer and a little bit in the Sapien layer. The other part of the simulation tech stack is assets. A lot of robotic simulation is empty because if you can't see anything, right, you need assets, you need objects, you need both visual and collision meshes. And for those who might not be aware, I have a great explainer for what these meshes are. I actually purposely wrote a section on our documentation just doing a quick 101 on simulation robotics. And this is what I mean by collision mesh and visual meshes. You'll actually, in the simulation world, you know, the visual mesh and collision mesh don't have to align. The visual mesh is what you see in the camera. The collision mesh is what the physics engine uses to decide how does a, you know, robot or object behave in the real world. Oftentimes they don't align. This particular mesh is used by Isaac Lab that we copied over, and it's clearly very, very different. And I can talk about optimizations we make around that later. But yeah, that's like the asset layer, right? Designing and modeling robots, modeling objects. Right below that is then the simulation framework, right? You need a framework to then, combine different technologies together, like the renderer and the physics engine. And that's essentially what like Isaac Sim is doing and Sapien is doing in many ways. Both Isaac Sim and the Sapien are both using the physics engine, which is a physics engine developed by NVIDIA currently, which also has a CPU and GPU variant. I can talk about parallel simulation later. And they also have their own custom renderers. I don't know what Isaac uses for rendering. I suspect also Vulkan-based, but Sapiens is a Vulkan-based renderer. And then I don't remember how to explain Vulkan, but Vulkan is just like a layer above the CUDA or low-level GPU code to render triangles and shapes and images extremely fast. And so the simulation framework wraps that together. And then at the lowest level, we have the code that's touching the direct GPU memory in many ways, right? We have the renderer and the physics engine itself, right? The renderer is for capturing images to show you what's happening, or if you want to do visual robot learning. And the physics engine is just dictating where things move if they collide with each other, right? Or how does your action at the task and API layer correspond to robot movement. And so that's like a kind of high-level overview of like simulation tech stacks. And other simulators will have very different ways of organizing things. Like Sapien covers the middle 3 layers. Simulators like Mujoko have a renderer and physics engine kind of together. Mujoko defines the physics engine and also has OpenGL-based code, if I remember correctly, for the renderer. And for tasking APIs, projects like Mujoko Playground will be kind of equivalent to ManiSkill. Yeah, so that's kind of like a quick overview of simulation tech stacks.
Yeah, I feel like one thing that's always impressed me about ManiSkill in particular, other than the speed, which you already covered, was the APIs. So it was nice that, like, you were mentioning that you thought that this was like, well, a necessary part, but arguably I've used a lot of these simulators and a lot of people do not put much effort into building good APIs or making it easy to design new tasks, like particularly the ones that didn't make the cut onto this figure, I think. Yeah.
I mean, I think it's a mix of how long the project has been going on. Like a lot of simulation benchmarks are released for research purposes, but only last for like 3 months, 6 months. There's not much incentive for those users, people to like continuously maintain and improve the API. ManiSkill's API has gone over like 2 rewrites from what ManiSkill 1, which was horrible to use, ManiSkill 2, which was slightly better, but had very poor documentation. And finally, the ManiSkill 3, which has a lot more documentation. I've painstakingly written a lot of it with the help of ChatGPT. And also a lot of redesign on some of the APIs to make GPU simulation easier to write in particular. The CPU simulation API is kind of similar, but we find at least the old Isaac Lab and the old Isaac Gym, they've improved a lot since. A lot of unreasonable API decisions that could have been better that we try to fix. I could show one example. This is not reflective of Isaac anymore, but this was what happened when we wrote the paper initially. This is just a comparison of a high-level review of the old APIs of Isaac compared to ManiSkill's current API. See if I can zoom in a little bit. So what we're doing here, just as a kind of example, is we want to take an articulated object, right? Articulated objects composed of many joints. Each joint has like an angle value determining how open it is. So we have a cabinet in each of these frameworks, Isaac Lab, Isaac Gym, which is much older, and then ManiSkill 3. And then all we want to do as an example task is to get the joint angle of one of the links. And that's basically it. And we also want to get the position of the handle on the link. And so the code is much simpler generally in ManiSkill. And even if you remove the comments I write for Isaac Gym M's and Isaac Lab, those are still longer. The other thing is our API is much more object-oriented and in some sense semantic. You will notice that the old Isaac Gym M's has a lot of code that has like magic numbers. Like if you see like there's a -1 here and 13, where's that 13 from? You have to know something about the robot itself to know what that 13 value is from. A bunch of other kind of magical numbers that are hard to explain. And you have to do some kind of like tensor indexing, right? This is what I like to call a tensor indexing nightmare. Right. This is why people don't writing batch code, and this is why people have gone over to Jack sometimes. Writing batch code is super annoying. You have to deal with batch size, you have to deal with batch operations, and you have to do indexing. So Isaac Gym had a lot of indexing you had to do. If you were a proficient programmer, no issue. If you aren't, hard to read. Whereas ManiSkill makes a lot of improvements where we do a lot of things object-oriented. There's like a physical cabinet object that you can use to access whatever joints you want, whatever links you want by finding them by string IDs, which is far easier to do. Isaac Lab made some improvements, but they still have some random like magic numbers that they deal with, particularly around like mesh processing. If you wanted to find the middle of the mesh, they actually hard code position, whereas we can actually generate a mesh object that you can then sample from. That's just like an example. And then just like other small things, this is like another very small one. I think Isaac Lab has already fixed this actually, where if you want to do like pose transformations, which is a pain, pose transformations in ManiSkill are chainable, whereas in Isaac Lab, you have to do method chaining on the right, which is much harder to read. You have to do a lot of nesting, which is hard to read, whereas on ManiSkill, it reads like a math equation, right? I'm taking pose 1 times pose 2, take the inverse, multiply with pose 2's inverse. Very simple. And that's kind of like some of the API design that we've tried to build on like past simulators. I personally have read a lot of the code for past simulators trying to identify the pain points. And from my own experience doing RL research, I often find these pain points because I try to run the code and I find something doesn't work. And I have to understand it more deeply. And so those are some examples. And there's a whole host of other things that I think other simulators actually learned from us, and that I'm actually it's awesome to see. Yeah, that's basically around that.
Yeah, so I guess you were maybe about to share the the feature comparison chart that you have on ManiSkill. So I think it's great to hear what you describe and you show visually, like just how I guess you abstract a lot of the way the dirty stuff that make maybe coding and simulation a lot easier, more pleasant. But I still I think it would be good for you to run through like each of these. Why do they matter for the end user of this simulation engine?
Yeah. So at this point, I guess we're now moving on to ManiSkill3 discussion. So ManiSkill3's improvement on ManiSkill2 primarily is parallel simulation, parallel rendering, and heterogeneous parallel simulation. You can look at which parts are novel. The ones that we have text and others don't have essentially is kind of novel. So I think the main thing is these days with ManiSkill3, Isaac Lab, and MJX, or the new MJX Warp, or Newton, as some people might have heard from NVIDIA that they're working on, which is a warp-based simulator, GPU parallelized. GPU parallelized simulation is the idea that on a single GPU, you can have thousands, tens of thousands of parallel environments all running simultaneously. And why do we want that? Why do we want to have high data throughput generation from a simulator? Well, it turns out reinforcement learning algorithms are very data hungry. If we can feed them more data per second, our algorithms solve the problem faster. So like if we want to train a robot to walk, right, in Isaac Lab, or if we want to train a Franca arm to pick up cubes, it's far faster when you have GPU parallelized simulation. Previously, if you want to do parallelization to increase your data throughput, you would have to use CPU parallelization. But CPU parallelization is notoriously very, very difficult because not only is your data on the CPU that has to transfer to GPU when you're doing reinforcement learning, right, using neural networks, you need a beefy server, and servers are less likely to have 100 plus CPUs, whereas on a single GPU, you can have thousands of environments very easily. So that's kind of what that is. A lot of the old simulators don't have GPU parallel simulation, and in many ways, it's very hard to use it. We directly use the physics binaries, and so we kind of like engineered it based on the physics documentation and code to make it as efficient as we can. Other people often have to build on top of Isaac Lab or Isaac Sim, or build on top of MJX when you start getting more overhead. And the second really big feature, and it's one of the biggest things that we released, I would say ManiSkill3 is the first one to have a more production-ready parallel renderer. There were some small projects from NVIDIA that did do parallel rendering before us. They did like, well, they call it tiled rendering. They did parallel rendering of like carpool or like ant environments, but those weren't really usable at the time, and they didn't have a general purpose one. What GPU parallelized rendering is like exactly the same thing, where we're going to have each of these thousands of environments all be rendering at the same time. And what are we rendering? We're essentially rendering camera images, right? Like maybe a 128 by 128 by 3 RGB image in each parallel environment. And why this is important is this unlocks a new scale of data throughput for visual robot learning, right? Previous simulators are often at a scale of like 30 FPS or like 300 FPS approximately at max. And it's because they don't have, optimized rendering that is directly connected to the GPU simulation, right? There's no device transfer now. And so we achieve like anywhere from like 10,000 to like 40,000 frames per second, which is 10 to 1,000 times faster compared to other simulators, depending on which ones you check. Some of them really do only render at 30 FPS. Some of them render at 300. We've made massive improvements on the rendering speed, and Isaac Lab followed suit. We released ours last year, and then they released theirs about 6 months ago. And funny enough, all of the major simulators have parallel rendering now. Mujoko has also released a parallel renderer in the form of called MJX Madrana. which is based on a simulator called Madrona, which is separate. And they released it about 3 months ago. So everyone's doing the same thing now.
So
that's
I guess concretely, basically, this parallelization allows you to nearly 1x what you used to be able to do with the same level of hardware.
10 to 1,000x. It depends on who you're comparing against. There are some simulators that are really slow. We ported over some of those scenes. If I remember correctly, I think Robotics on their paper, their FPS is like 40 or 50 FPS. It's quite slow. And if you use some really old simulators, like RLBench or AI2 Thor, it's even slower. And so with that massive throughput, you can do a lot of things like domain randomization, like at new scales. Like, for example, these are just like 2 environments. There's a push T environment, a very famous environment now, and there's like a cube stacking one. I actually have like 1,024 environments being run in parallel. I'm just showing 4 of them. Each one of them has like different colors or different camera positions. So you can actually like train your policy to generalize across these variations. And later on, I'll show one of our demos, our sim-to-real demo, which leverages this feature very well to do 0-shot sim-to-real.
Got it. Yeah.
The third feature that I'll mention that's a little bit more niche, I think most people don't actually really need it entirely, is called heterogeneous GPU parallel simulation. What is this referring to is essentially like in each parallel environment, we are allowed to support a different number of objects, articulations with different degrees of freedom, like they have a different number of joints simultaneously in parallel. We have one common task we often show to kind of show off this feature, which is this environment. This is actually ported over from ManiSkill3. In fact, this is one of the original tasks we built. We've now upgraded it to GPU simulation and parallel rendering, and it solves like 10 to 50 times faster now. And what's unique about this is I think currently Isaac Sim or Gym or Lab still doesn't quite support this. And maybe they'll add it in the future, but they don't support having like heterogeneous simulation where every cabinet that we're trying to open with a robot is completely different, right? There's different textures, there's different shapes, there's different collision meshes, visual meshes, and there's a different number of joints each. And the way we do it is not super interesting. What we do is in PhysX, we just pad everything as much as we can. And then at the ManiSkill layer, we're just doing a lot of indexing for the users ahead of time so they can still access data of all these cabinets in an object-oriented manner. Like, for example, I can have a single object called link or drawer that represents a particular drawer on every single cabinet at a different location. And I can access a joint angle of that drawer for each cabinet in parallel, even though each cabinet has a different number of drawers and doors. And so we did some work on that. It was pretty cool. We have yet to do a lot of sim-to-real testing for this environment, but we hope someone with a fetch robot could do it. Those are unfortunately discontinued, but I know one lab at UCSD has one, so maybe we'll work with them. So that's what I mean by heterogeneous simulation. And on the right, there's another example. Each of these tabletops have different objects sampled and a different number of objects sampled per tabletop. So this is like a clutter picking task that's actually quite difficult to do from vision. And each one has a different number of objects. And so this is more ways to kind of really robustly test your model when you're doing training to have a lot more variation than you can usually do in previous GPU simulations. So that's heterogeneous simulation. And I think the main claims to fame for ManiSkill3 is really like the simpler API, parallel rendering, and heterogeneous GPU simulation. Most of the other aspects are things that we had before or other people have, and it's not so interesting, but I'll quickly go over them. Some benchmarks include demonstration data, like pre-collected demonstration data so that people can do imitation learning research or RL learning from demonstrations research. I think this is false now. I'm pretty sure Isaac Lab has demonstration data sets now. Previously did not. But a lot of these benchmarks don't have it, so you can only do certain kinds of research if you don't have that data.
So are these like teleop human doing stuff in your simulation environment and ask them to do some task?
Well, we have a mix. We have multiple tools for collecting data. The most common tool we use that's the most scalable is motion planning. What is motion planning? Motion planning is like an open loop way to control robots where you define a sequence of key points and you have the robot follow them. So for example, if I want to pick up a cube, I would define a key points of like pick up the cube to drop or something, right? And you will generate like 1,000 or 10,000 demonstrations. We also provide teleop tools to collect things by hand. We're much slower, so we don't really do that much. Yeah, and if I recall correctly, RLBench also does motion planning based. We were inspired by them to do the same solution. Realistic object physics, this one is variable. Different simulators have different levels of precision, to be honest. Like if you're comparing Mujoko and PhysX, just different levels of realism. But in general, we put X for Habitat and AI2 because they don't support low-level physics. What happens for them is that if your robot touches an object, the object attaches to the robot. So you don't actually have to graph the object. That's what we're comparing. A photorealistic rendering, this one is iffy to be honest, but this is just checking if these simulators support ray tracing, which is a form of realistic rendering. Room scale scenes is just scene data sets. We have a Robotics data set actually. We also have Habitats data set and AI2's data set in our benchmark. Visual RO baselines, basically very few have these because the renderer is too slow in some of these benchmarks. And even if they do have these baselines like Habitat and AI2 Thor, they run too slowly. So the only fast ones really run are ASIC Lab and ManiSkill3. And the other ones, I guess I can encourage readers just to read about them. For the sake of time, there's like too many things to explain. But
sorry, Stone, can I ask you about the so-called realistic object physics, right? So, you know, some of these like mechanical system in the real world sometimes are extremely sensitive to initial conditions. So let's say if I were to drop a pen on the table, like where, you know, the pen will land depends heavily on the initial condition. So when you say realistic object, is it like sensitive to the extent? Or
there are definitely many real world phenomena that we cannot simulate. Like for one, soft body simulation currently is pretty weak. I mean, we have warp-based soft body sims that are really cool and powerful. But like in terms of accuracy, it's very, very hard to model real world cloth, real world deformables very accurately. We're almost always approximating things. For rigid body simulation, which is the main focus of ManiSkill3, and that's what we kind of parallelize a lot, it's much more accurate enough that we can do sim to real, and I would love to show the sim to real demo later. But there will be certain dynamics that are heavily dependent on things independent of the physics engine, actually. Like, for example, if you don't model the object well enough at the asset layer of the framework, it's not going to simulate well. Like, for example, some people will, if you, like, let's say we look at this cup. If you don't model the hole in the cup is not a cup anymore, right? It won't work correctly. Another thing is we can only model things up to a certain amount of precision, really. If you try to make it super precise, the simulator gets really slow and unpractical to use. So oftentimes in simulation world, we're often trading off simulation accuracy with simulation speed, actually. You often never get faster speed and accuracy. That's usually something that's not possible without fundamental improvements on algorithms. Like even between the physics engine that we use, between the CPU simulator and GPU simulator, there's already some small differences. The CPU simulator is slightly more accurate than GPU simulator. GPU simulator is much faster, and so we still love to use it, but it will have some small inaccuracies from.
Got it. Yeah. I mean, you mentioned about this trade-off between accuracy and speed.
Yes.
I also like your take on just the diversity of what you simulate, right? So I think it's great to see all this parallelism, you know, across like just different objects and maybe so-called similar tasks, but just maybe varied. So I don't know, like I was thinking one in like maybe layman version of this I keep thinking about is in theory you can speed up time in simulation versus obviously the real world, and that's always the appeal of simulation, right? But then again, like there could be nearly an infinite search space or exploration space, you know, all kinds of lighting conditions, like even cups, like there's so many different cups, right? So I wonder like how do the practitioner actually do it right now in order to make it somewhat tractable so that let's say the stuff that you collect in simulation is kind of representative of the actual distribution of things that you may observe in the real world. You know what I mean? Like it feel like if I were to let's say use simulation to get a robot arm to fry an egg, I can literally think of almost nearly an infinite way to simulate that.
Yep.
And so is that how do practitioners who use this simulation engine do that trade-off today?
Yeah. In fact, I would say in the world of simulation, the biggest downside of simulation is diversity is hard to achieve if you don't know how to do it. What I mean by that is you can actually achieve a lot of diversity in terms of asset textures if you use Gen AI, for example. The Robotics project from UT Austin and NVIDIA is actually a great example of this. They use Luma AI's 3D generation tool to actually sample a bunch of random objects. And they have like a data set of like 1,000 objects. You also have Optiverse. There's a bunch of other data sets out there. That is the way people try to scale diversity, I think, right now, where they just zero-shot or one-shot generate a lot of object models, and you train on all of them, essentially. That would be the hope. Another approach that is quite interesting, people at Pulkit Agrawal's group at MIT, Abhishek Gupta's group and UW, I think some people in the Fei-Fei's group and Stanford, they're exploring real-to-sim training. What they do is, okay, maybe we can't generate things. We don't know what to generate. Let's say we don't know what to generate. We could use a real world scan of our environment or scan of the objects that we have in our box that we want to, let's say, pick and place, generate those in simulation and make digital twins, or digital cousins is another term people like to use. That is like representative of the real world distribution in some sense. We're not going to simulate everything, but we're going to simulate the things that we have captured already in the real world. And some people also even go as far as modeling simulation physics and parameters, like they'll tune the friction parameters and density parameters accordingly based on real world rollouts. I don't remember the paper name, but that's a really cool idea where they'll have a robot in the real world push an object over multiple times and use data collected from that to inform how to simulate the object more accurately. And so these approaches are more targeting like exact replicas. This is one approach towards, getting that diversity. Another approach, which is what I was mentioning earlier, which is the Gen AI approach in some sense, is really mostly about what we call domain randomization. And we want to achieve generalization by brute force. And this is what has worked for locomotion. And that's why I think people want to do for manipulation as well. What I mean by that is for locomotion training, like, you see Tesla walking around, you see those humanoids walking around, those quadrupeds walking around. Those are all trained in reinforcement learning these days in Isaac or other simulators. And what they do is they do a lot of perturbations in simulation. They'll push a robot around. They'll modify the joint parameters, the simulation parameters randomly so you can be so that regardless of what the real world conditions are, we've probably seen something similar in simulation, right? We're achieving generalization by brute force. Similarly, for manipulation problems, which I'm very interested in, another approach is we're basically doing the same thing, right? We're going to randomize the camera position. We're going to randomize a lot of the dynamics of the object we care about. Like, instead of modeling the friction perfectly, let's just randomize the range. Let's make it possible that it can pick up a cube that's a wooden material as well as an ice cube material. That would be the hope. And then similarly for like textures, right? You can also do texture randomization. We can make the cube color random. We do that for a sim-to-real demo. Or you can do the Robocasa approach and many other papers where they sample a bunch of assets from Luma or any other 3D generator.
So in your view, do you think this brute force approach eventually will give you enough examples to be a fair representation of the actual distribution you may still see in the real world, right? I mean, ultimately, that's what you want in order to get zero shot sim to real, I suppose.
Well, I guess a reverse question actually for you is, do you think video generation models or image generation models are reflective of the real world yet? Do you think they will be?
I think they are already in some sense. I think the question I have is still, what if you have such a model that can, like, you still need to kind of tell it to, okay, simulate what, right? Like, so, like you say, I guess you call it domain diversification, something like that. And so, is 1,000 objects enough? Like, because in theory, you can do 1 million objects, or maybe even more. So when is it enough? Yeah. What's your sense?
I think for one, I'm 100% sure the amount of range that we can randomize in for textures and model and meshes is sufficient. Like looking at current image generation, video generation models, they are really good. We will probably get there for 3D generative models for generating meshes. I'm not an expert on that,
progress,
but like getting there, right? We're getting to the diversity we need. Now the question is a problem of sampling. Which of these things in this giant set of possible samples should we use? And that question is very, very much unanswered. It often depends on your task. Obviously, I would argue the more the better, but it is unclear like how much we need, right, until we get generalization. Some people might say 1,000 different objects. And the question is, how different are these objects, right? It could be 1,000 different cups, and then you're not going to generalize to like a bag. So it's a very open problem. I don't know the answer either, but people want more objects in general. Like the more the better, right? And the other thing is, simulation in Gen AI is compute scalable, right? This is one of the biggest reasons why I want to work on simulation. Because of the compute scalability, for the most part, I think simulation is here to stay. It's very, very hard, in my opinion, to scale real-world data. And yes, there's been great successes so far from like Pi and Gemini Robotics team, right, for the VLAs. But there are still limitations to those, right? The success rate or reliability might not be high enough. And we hope that simulation is what's going to bridge that gap of reliability, going from 10%, 50% to like 5 nines.
Yeah. And the simulation has like really clear wins in a few areas, right? Like locomotion, like a locomotion in particular. And to a lesser extent, it's doing very well in things like grasping. But like, there's still plenty of spaces where it feels like sim to real is not quite there. Like, particularly when it comes to like semantics. Like, what do you think about that? Like, I guess part of the answer is Gen AI, like creating assets to specific tasks and so on.
I think sim to real manipulation is definitely very, very far away from being solved. Traditionally, people actually have relied on depth sensors because simulation depth images look very similar to real world depth. People recently are trying RGB now, like my lab as well as NVIDIA and the Mojoko team, where they use parallel RGB rendering and do domain randomization to get sim to real manipulation. We're very early stages, and actually, in fact, the last 3 months or last half year has been the first time we've ever been able to train models so fast with large-scale randomization to do zero-shot sim to real from RGB images. Previously, it was often depth images or very, very slow training.
It does seem like stereo also is doing really well. Like we'll talk to Dextra next week, I think, about that.
Yeah, they are using stereo vision and it's helped improve the success rate a little bit. Our sim to real demo as well as Mujoko sim to real demo is actually just zero-shot one camera, but all are possible. Yeah, there's a lot of open problems, like for sure. We don't know how much diversity we need. And I think in terms of sim to real, the biggest gap primarily is still visuals for rigid body. For soft body or deformable manipulation, it's physics and visuals. But for rigid body, I will say primarily it's a visual problem. How can we randomize? The question is like, I mean, we're still exploring right now. Now that we have GPU parallelized rendering, right, what should we be randomizing? How much should we be randomizing? Like, for example, I could randomize a camera everywhere instead of just within plus or minus 5 centimeters. Who knows, right? I think with the release of our parallel renderer and NVIDIA's parallel renderer and Mojoko's, now we've actually opened a very new avenue of research that previously would have taken hours or days to train.
Yeah, I guess in some ways it's a good problem to have, but it strikes me that maybe the bottleneck towards using tools like ManiSkill3 and all these updates to parallelization to the other engines as well is who is the researcher who is going to dictate what to simulate, because now you can simulate so much, because otherwise you could waste compute if you end up having a diversity that actually doesn't matter in the real world, and then you miss all the diversity that actually you really need to do it. So and it seems to me it's very hard for anyone to, it's almost like you kind of have to feel the simulation AGI or whatever you call it. It's a gut feel, and there's a very, very few people in the world, in my, like, I don't know, it's just my guess, that actually know how to feel it.
Yeah, I will say there's very few teams in a world that actually understand simulation deeply. I would say like my lab, NVIDIA's physics team, Mujogo's physics team, and a handful of startups around the world understand simulation at the physics engine layer and renderer layer. There are more people who can build environments on there like me, but that's also quite rare, right? People don't teach simulation in school. They teach machine learning. So imitation learning is so easy. Explosion and growth for like the robot support for imitation learning and Hugging Face is because everyone learns machine learning and supervised learning. So, using those PyTorch tools and MSE loss function or whatever is pretty easy to understand. Simulation, on the other hand, is actually a graphics problem in many sense. You have to understand how to model things. You have to understand why things don't work. Like I learned Blender to build ManiSkill3. I actually had to learn that. I remodeled certain meshes. I actually helped the Hugging Face team model some of their gripper meshes to be convex so you can simulate them properly. But that took like a year and a half of me just learning that. I've been working on this for a year and a half now, ManiSkill3. And I'm very grateful for my co-author, Fanbol, who's now at Hillbot full-time, my advisor startup. He taught me a lot of the trade on simulation tools. I mean, he is the creator of the Sapient engine as well.
Yeah. So while we in theory the compute can continue to scale, we need to also scale people like you, Stone, who actually now with all this powerful tool, otherwise you'll be like, wasting GPU, if a fella don't know what he's doing.
I feel like the right answer to this is if we can make sim to real work super seamlessly, better than before, we'll get more people on board. Everyone's studying imitation learning now, but we can get some people to study simulation and reinforcement learning more often, right? And that's really dependent on the success, real world successes, right? We're just going to be like, top down trickle effects essentially that we want to help.
Yeah, maybe this is a good segue for you to show some of this video that you have, like actual sim to real.
Yeah, I guess I can talk more features about ManiSkill3.
Oh yeah, sure.
One of the other things that support that sim to real demo that I'll show in a second is primarily that we optimize a lot for memory, actually. And this is actually part of my interest in like intersection of machine learning and simulation research. I often find that for reinforcement learning, especially visual reinforcement learning, GPU memory is like gold. You want to use as little of it as possible in a simulator. And so I think currently still we have the most efficient memory usage of all the parallel renderers, I think. Like we use like 2 to 3 times like less than Isaac. And so you can actually run all these experiments on one GPU on Google Colab even. Maybe
how do you achieve that?
It's just a lot of engineering design on the Sapient engine itself. Actually, one of the things we did is we stripped out a lot of the unnecessary features of a renderer. So we have like different shader options. One of the shader options is called minimal. Only renders like very, very basic RGB and depth. It looks like this. It doesn't look realistic at all. Like there's no shadows. It's just images. Oh, this one has shadows.
Wait, you're not sharing. Are you trying to share something?
Yeah, I got to share again.
Yeah.
It's like very, very basic RGB and def. We're not rendering albedo or normals or anything our old renderer used to do, and that saved a lot of memory. Otherwise, it's a lot of engineering tricks on the Vulkan side to like just save it in general. It's like this is like the renderer we're using. There's like no shadows. It's very minimal. And this is quite different from the approach that Isaac Lab is doing. I think Isaac Lab by default has ray tracing enabled for the parallel rendering. And so they have I suspect that's why they have a much higher memory usage than us. So they look slightly more realistic, but slower rendering. And so one of the cool things this enables is that, actually during the Robot Hackathon, people have trained our Sim to Real demo. They followed a tutorial for doing Sim to Real. And I'm gonna go find the video. Give me a second. Do you see this video of the robot? Yeah, so this is the SO100 robot designed by the Robot Studio in Hugging Face. That's like $100, very cheap. Actually quite hard to do sim to real on because the joints are very inaccurate. So during the Robot Hackathon, people will actually use our simulator, train it in Google Colab for about a couple hours on a pretty weak T4 GPU and get sim to real transfer success. The example I'm showing here is trained on a 4090 for 1 hour using highly randomized visual randomizations and ManiSkill3, and we get like 0-shot sim to real deployment. And this is just an example of a cube picking policy.
You also, I assume, have to do like dynamics randomization to handle the slop in the joints. Yeah.
We do randomizations on the joints. We do randomizations on the cube friction and the cube size. So I test on the same cube here twice, but it actually generalizes to different colors of cubes, different shapes of cubes, and also has a very large spatial randomization. So I actually randomize the error about like 30 by 30 centimeters. And why we're so interested in that, because compute is scalable in simulation. I don't need to collect demonstration data to do this. Demonstration data will help. But the larger your randomization area, the more demonstration data you need. So this is one of the main advantages for simulation. Obviously, the caveat is you have to model this thing in simulation a little bit. Modeling robots and objects is kind of hard, but once you do model it, you can get very fast, I'll say, manipulation behaviors. I say if you do imitation learning on this, it will probably take much longer to actually solve the task. And this is what the training looks like. It looks nothing like the real world, really. But we're doing like massive domain randomization here. So you can see that we're randomizing the link colors, the cube colors, and this is all visual randomizations. And it's hard to see, but we're also randomizing the camera extrinsics and intrinsics a little bit. And perhaps even harder to see. So we're actually showing in multiple views. Let's see if I can zoom in on the training images. So the one with the orange table background, this is the raw simulator output. The main trick we use to bridge the sim to real gap for a 0-shot sim to real demo is using green screening. You'll notice that the background and the smaller image here is the green screen applied to the segmentation map that we use above here. So basically what we're doing is we're going to green screen everything but the robot and the object of interest. And so as a result, tiny 128 by 128 image looks actually kind of realistic. And when we train on that data, it covers so much of possible images that in the real world images are in distribution suddenly, right? We have examples where the robot is a white color, a black color, orange color. We have examples where the camera is slightly shifted to the left and right. So if the real world is perturbed a little bit, it's fine. And we do this training for about 1 hour on a 4090, and you can get 90% plus success rate if it's calibrated correctly.
Yeah, but I guess during the actual deployment, the camera angle is roughly what you also sample from the simulation, right? Even though it doesn't have to be precise.
I don't actually have to do accurate sampling, so I'll show you how rough it is. It's very rough. I think people who are roboticists might remember the days when they're doing camera calibration. They're often using checkerboards, right?
Yeah.
This is super annoying. I hate doing this. I suck at doing it. I don't want to do it. This is like, honestly, if I want people to try doing sim to real and they have to do this, I don't think they will ever try it. So what we do is we make a very simple tool where we simply ask a user to position the real world camera to line up with the simulation one. And what we do is we show them an image with both the images aligned up together. So this is the real world image on top of the simulation image. And all we ask is that you get it approximately lined up. And this is how well lined up it is. It actually has a lot of error. You can see for one, we don't model wires. This link is slightly off. This back part is slightly off, right? There's like some amount of error. But it's perfectly fine because, in simulation, we're doing large scale randomization and we're randomizing things that we just can't estimate in the real world easily. And so as a result, it's quite easy to do the sim to real setup. It takes like 2 to 3 hours to do entirely. My camera calibration time takes like 2 minutes. I will quite literally, and I did this at RSS2, I brought the camera out, put it on the ground, moved it around for 2 minutes until it looked approximately correct. And here's another example. Like it's very far off. but it's fine because we're doing large scale simulation and large scale visual simulation to, you know, cover all these randomizations essentially.
Mhm.
And
So this 1 hour in 4090, roughly how many, like, I don't know what is the right way to think about it. Like how many time would it have, like, the speed up time, you know, across all these various things that you're randomizing, like a different camera angle, you know, slightly different joints, different objects, color and whatnot.
are you asking how long it takes to, how many environment samples, or how long does the training take?
Yeah, no. How long? Sorry, how many environment example? Yeah.
So we train for 1 hour, and that's approximately, let's take a look. So these are some of the successful runs that I trained at RSS, actually. Let me just hide the ones that are fine-tuning checkpoints. Nope, this is the wrong one. Also the wrong one, sorry. There we go. So we're roughly like collecting almost like, so the policy starts getting like 90% success rate at around like the 35 to 40 return mark on the reinforcement learning training. And that's about 40 million samples in simulation. So on average, from my multiple runs and testing, I would often collect about 25 to 50 million samples in simulation before I deploy it successfully with pretty high success rate. So that's like, and also at every time step, we are randomizing a lot of things. So you can imagine it's about like several millions of different color variations, small differences essentially. Yeah, on order of millions.
Okay. Yeah, I think that's a great number to just for a layman like myself to think about it. Like, I mean, this is like as if you did the whole thing 50 million times.
Yeah.
Other different scenarios.
I will
Obviously,
argue though,
yeah.
my own experimentation, you don't need to randomize that much, actually. The reason why it's being randomized so much is because we're doing reinforcement learning. I can limit the diversity a bit more. Like, I can reuse colors more often than once. Right now, I'm not reusing colors at all. I always sample new ones, but I could reuse them. And I think the performance will do fine. The reason why we collect so many samples is because RO has to learn from trial and error. So it spends a lot of time just learning that, essentially. Yeah. But a million is a good mark. A million is a good number. More doesn't hurt.
I guess it also gives a rough sense, like with a consumer grade GPU, 1 hour, what do you get in something like ManiSkill, right? For tasks like this. Okay, cool.
I will also point out, I love how people like to say 4090 is a consumer grade GPU. In my opinion, it's not really. Because the other thing I want to know is that 4090 is the best GPU for simulation, actually. 100s, H100s are more costly, but not better.
Yeah.
And that's because,
because
4090s have ray tracing cores. They have parts of the GPU dedicated for rendering. And Vulkan will optimize the hell out of them. If you use H100 and A100, they actually render much slower. Yes, they have high memory capacity, but they render very slowly, and so they're not
I
worth
see.
using.
For
49 is a higher
simulation
clock
that
speed,
requires...
too. Yeah, they're just faster.
Yep.
Yeah.
Got it. Because you have rendering, you need to take snapshot of actual visual output. And all this, like,
Yeah, despite being a consumer GPU, they're actually the best one to use.
Yeah, what you want is gaming consumer GPU, like the best one.
It is the best gaming GPU, right? Like, it's a really
you got 5090
consumer
these days,
GPU,
so...
but yeah.
Yeah, so that's kind of like our sim to real demo. We have another video on my Twitter account and also on our website showing like an uncut run, max speed, where it does like 19 of these cube places like in a row successfully, and we stop it when it fails. So this has pretty decent reliability. I might actually try it. Oh,
pretty representative of the success rate, 95%.
Is it representative of the simulation success rate?
The real world one, the real world success rate. Oh, sorry, was this all simulation that you're talking about? Yeah.
No, I'm saying in the real world, the success rate is like 90% plus. I would run it like 20 trials and like 19 out of 20 times it will pick up the cube.
Yeah, nice.
We also did some experiments, although this really depends on your system ID, where you align the real world to simulation. On our previous setup with the Koch arms, which is like an older version of the Hugging Face low-cost arms, let me see if I can find it. This is the... I want to use a B2 paper. This is the outdated one. Let's see. We actually try to check the simulation and real world success rates and see if they're similar, and they actually are kind of similar for a very basic task.
That's interesting. Yeah. The basic task, the same cube task. Oh yeah, graphs lift and return.
We check 2 successes. We check an intermediate success rate where it graphs the cube, and then we check whether or not it lifts the cube up and returns it to like a predefined rest position. And the simulation success rate and real world success rate are pretty well aligned, actually. Yeah, and then we also even tried this over 3 Cs. Like, we did a lot of evaluations. Every single checkpoint we evaluated, like, I think 8 times, and we have a total of like 3 Cs times 20 checkpoints each of like 60. And this part of the project was led by Xander, one of our undergraduate interns, and with me, and we did a lot of like testing on this. And it was quite cool to see this result. It's not perfect though, but it was quite cool to see. All right.
Yeah. So I guess.
Oh
yeah,
yeah, go
sorry,
ahead.
Chris. Yeah.
You go first.
Chris, you go ahead first.
Well, I
you
was
can go
going to
ahead.
ask. This is a little bit of a change of direction though. So if you want to ask about this, go. Okay,
No,
I was gonna.
Yeah. Okay.
If you're a final year PhD student, right, or close to it, what is going to happen to ManiSkill? What's ManiSkill's
gosh,
future
it's
look
the
like?
exact same question I have, man. I was like,
Okay.
what incentivizes you guys to keep reading? And there's not just ManiSkill, right? There are all these Robocasa and different
Yeah.
projects. Like it seems to me there's a diversity of like tools and what motivates teams to do this.
I'll say most teams are not. You'll see like a lot of projects out there. The last commit was like a year ago or many years ago or many months ago.
Yeah.
For ManiSkill, like the last commit was like a couple days ago. So I'm still maintaining it. But no, it's a very valid question. I think it's a little bit up in the air what I will do with it, because after I graduate, I obviously will have much less time. Maybe I will do it on my free time. I don't know. Especially if the product becomes even bigger. But it's hard, right? I mean, I have a work-life balance, right? I have a girlfriend and I have sports and I do other things. So it will get difficult to do that. I will say one thing that at least during my PhD that motivates me to do it is kind of based on my advisor's advice to me when I first started. His advice to me was to very much focus on aiming to not only do good work, but become the number one or top 3 people think about when they think about your research area. And that's kind of what I'm aiming for. Like I'm thinking like if anyone thinks simulation and reinforcement learning, I hope they think of me. And I guess the fact I'm on a podcast maybe is working a little bit. I've reached the
No, for sure,
podcast
man.
levels of fame. So that's kind of one of my motivations for maintaining a long-term project. I've personally felt like when I maintain a project so long, I increase the quality of it. Yes, I'm publishing less papers, which is kind of antithetical to a PhD to some extent. And, I'm making improvements on the paper that I'm not submitting, actually. I've added a lot of things to ManiSkill since the original research submission, since the original release. But amount of motivation is that, to become someone that's recognized as an expert, you want people to be using your code. You want people to be asking you for help whenever there's a bug. Not that I purposely leave bugs in the code for people to ask questions about, but I'm often responding to issues. I'm often the first people see when they use our project. And so I have like a very public profile now, essentially. But yeah, by maintaining it for such a long time, it's been like a year and a half now. I've been on the project for much longer than that, but as a lead, it's been a year and a half. Building that reputation, I think, is very important in some sense for my academic profile and also furthering research in many ways. And it's also a great way, if I maintain it for long, to find issues that other people have that could spin up new projects. So that's kind of like my motivation for keeping on it with the PhD. I'll also point out another thing. This project is now partially affiliated with a startup. My advisor runs a startup called Hillbot, which is also very focused on simulation-based training for foundation models. And so it is possible that in the future, they may hire an engineer to maintain it when it wants on, right?
Yeah.
As one possibility, they've considered that. We haven't done it yet. We do have a simulation team at Hillbot that is maintaining the underlying engine, at least. So the public version and the company's internal version is being maintained by the sim team. The ManiSkill part is only being maintained by me at the moment, or primarily by me. There are other people who help out. We've also reached a stage of open source where people that I don't know personally have been contributing PRs, which is great.
That's nice, yeah. Self-sustaining. Hopefully it reaches that point where it's actually self-sustaining, but yeah, let's...
We'll see. Yeah, we'll see.
Yeah, I think it's such a incredible thing you guys are doing. Like it's, I mean, simulation is going to be a very, very, very big part of like embodied AI.
Yep.
And I'm glad the folks like you are betting on simulation. You can't everyone just go and do teleop because teleop works for now. And then if everyone just do teleop, then only the big boys who have the resources to teleop can do it, get a big warehouse and do it. I think it leveled the even playing field a lot, especially with all these APIs that you're making it. I mean, just looking at the lines of code, it's just so much shorter than the one, let's say, from Isaac. I'm surprised though, like I would have thought that NVIDIA will make the best out of it. But anyway.
We're doing more for sure. It's a lot better than our paper. Our paper was like released 6 months ago. So in that time, they've improved a lot, actually.
Got it. Yeah.
I will also add another thing. Another reason why I'm very interested in simulation is also for robotics evals. I actually, I have no idea if simulation data is ever going to be used for training. But at minimum, a lot of companies these days who are doing VLAs, they need a way to scalably evaluate their models. Currently, video generation models are not accurate enough, and then simulation has already been used for evaluation. We did a project in my lab with Google last year, investigating this exactly, and it's one of the most commonly benchmarked environments now, called Simpler. I have some interest in making it bigger, but I think at least it's there to stay for evaluation purposes. Right? That's another interesting viewpoint I have for simulation research.
Yeah, I think simulation my own take is that it will be used for both like data generation and also eval.
Yep.
Eval, I don't know. I kind of feel that you definitely should do eval in simulation, but ultimately you still need to test it in the real world. I mean, this is
both.
robotics after all. Yeah, right. You
Yes.
still need to test things, but before you put it out there, yeah, eval in simulation. Yeah, sort of when it fails, it's fine, right? And
Yep, definitely.
yeah.
Yeah. One last question I have. All right.
Mm.
So we're talking about sim to real domain randomization, all this. One thing that I always wonder about these demos is how sensitive are the domain randomization parameters? How much tuning do you have to do to get it to work the first time, right? Like the transfer at your 95%.
That's a really good question. I wouldn't know because I think for our Central demo, my undergrad intern, Xander, he was the first one who did it.
Okay.
All I know
so it's
he-
free because it was undergraduate labor, so 0. All right.
So I have no idea. I took his parameters and modified
Right.
a bit more, and it worked
Yeah.
well for me. I just know vaguely while we were doing the project discussion about the sim to real stuff, we initially started with just cube shape and color. We added friction a little bit later. And then camera randomizations as well later as well. Definitely, we did notice a very noticeable improvement from doing camera randomizations. My own experiments have shown the same. If I don't do the randomizations, it doesn't work so well, especially because I'm not aligning up the camera perfectly. So that definitely helped quite a bit. But it's also like a bit of an art. Like I think the Dextra RGBH paper is also kind of heuristically defining some domain randomizations, like initial and final conditions, and doing like a schedule between. It's an art, I think.
Yeah.
I do want to advocate for more people to explore more automatic curriculum learning methods that you like, let's say the value function of the reinforcement learning model to like guide your randomization process. Some automatic ones recently that I remember, they're maybe less principled, like Eureka line of work from the keyboard lab, which is Ma. They use language models, right, to decide randomization methods. Or that was Dr. Eureka, I forget which one it was. But similarly, there's a lot of open room to explore around curriculum learning and randomization ranges, right? You want to start from an easy task and then go to harder tasks, or you want to decide, how hard is too hard.
That's interesting because this does feel like the big, like, open question to me, and a lot of this is like how hard that is, how like well defined that distribution has to be, and maybe it's possible that there's just some common set that common set of parameters. I assume it does get easier to apply to a new task, so maybe it is just not as big of a deal.
Yeah, I hope it becomes like PPO parameters. I think everyone uses very similar hyperparameters. They use the same rate, they use the same architecture. Maybe it will converge on that.
Yeah, makes sense.
Yeah, so I guess maybe as a wrap up, do you? I know you may not work on ManiSkill forever, but if you were to continue like helping out on ManiSkill, let's say for ManiSkill 4, let's say the next one, what kind of improvement would you want to push for, or would you like the community to contribute, like to get it to?
That's a great question. It's actually the most popular question I've been given at RSS. During my presentation at RSS, someone in the crowd asked that question. And every time someone's met me that I didn't meet before, that was the first question they ask at times. I think there's two aspects to consider. You can either consider applications or performance. I think applications being like sim to real, scaling evals, stuff like that, and performance being like making the simulator faster. I think performance-wise, we are already close to some limit, like in terms of GPU bandwidth in some sense. We're already hitting some limits a little bit. The renderer could be faster for sure. I am aware there's some possible optimizations that we have not done or released. The physics engine, I believe, can be faster as well, particularly because we're using physics' GPU version. It is anticipated that NVIDIA's new Newton simulator, or the MJX Warp simulator, will be much faster. And I'm very, very excited to help possibly integrate that once it's released. I think their API should be similar. I'm very familiar with them. We definitely want to have Newton as a possible backend. And we trust the NVIDIA team a lot to like make good software. They made PhysX, which is, I think one of the best simulator engines out there. It's very flexible, very stable, which is often the most important part of simulation. So that's kind of one aspect of the performance part, but I think we ourselves don't have much power to do that. I think we are kind of just waiting for NVIDIA to do something better with Newton. And once that's released, I'll probably just add it, but we probably won't release another paper just for that. In terms of actual research, there's kind of two directions. One of them is further pursuing that zero sim to real research. Since the sim to real demo I showed earlier was zero shot, but I think it's very powerful to try to consider, can we do adding real world demonstrations? Tally up 1 or 2. Instead of 50, click 1. And use that to help align the simulation trained model to the real world. Another really powerful consideration is that because we're doing reinforcement learning simulation, it should be easy to transfer to doing real world reinforcement learning without having to change the loss function. If your loss function doesn't have to change while you're training in one environment to another, it just makes things a lot easier, right? There's actually been a lot of research in the past where they try to take imitation learning models and try to fine-tune the reinforcement learning later, and oftentimes the performance just plummets. Part of the reason is because of the objective mismatch. The loss function is different. People have tried to fix it in recently with different ways. I'm really excited to explore them. There's one called like diffusion PPO, all kinds of PPOs.
Sure.
But another consideration is, could we just do sim RL and real world RL? And the great things about doing this approach is that real world RL has traditionally not been possible because we often only have sparse reward functions in real world. Sparse reward functions make it impossible to do reinforcement learning because reinforcement learning is bottlenecked by exploration. If I'm not being told at every time step how well I'm doing, I'm only being told that at the very end of a task, very hard to solve. But if you have a pre-trained sim reinforcement learning trained model, maybe that policy gets you 90% of the way. Like for example, currently my sim to real demo gets like 90% success rate-ish. Plus or minus 10, 5. It's not 100% yet, or 5 nines. But, it gets 90% of the way there. And we can use real-world RL to fine-tune it a little bit more to be better adapted to the real-world images and the real-world dynamics, right? And that could be quite interesting to explore. And I think real-world RL is already making a comeback. Quite a few people are working on it, especially Abhishek Gupta's group at UW. They're doing a lot of really cool work on real-world RL. I'm very interested in trying it in the future. The third kind of arm of research is evaluations. I think we had an existing simpler project, which is a set of like 8 environments that looks realistic, and you can test all kinds of open source VLAs on it, and we show that the success rate in sim is correlated with the success rate in real, and that the ranking of models in terms of success rate is actually the same in real and sim. That only has 8 environments, not a very big test of generalizability, and it's also primarily still based on ManiSkill2. We ported some of it over to ManiSkill3. It makes evaluations even faster, but we need to clean up it a lot. So cleaning up that project a bit, and also trying to find a way to scale it so that we can have like thousands or tens of thousands of environments without having to model each one individually is a very interesting project. Like we want to build like maybe a simulated version of RoboArena. RoboArena is a recent project from many people in Berkeley and some members of Pi where they have, a chatbot arena robot evaluation benchmark. But that's real world only, which is obviously limited. We are thinking about ways if we can do the same thing in simulation and scale it up somehow.
Okay.
Long-term research project though. Very hard problem because we got to do a 3D reconstruction, and I don't think the 3D reconstruction technology is even ready yet. We have to innovate.
It's getting better, but not quite. Yeah, very cool.
All right. Well, thank you so much for the sharing, man. Stone. It's certainly very, very eye-opening for me. Maybe just as a last question we always ask, are there any like recent papers that you saw? I guess it doesn't have to be recent, but any cool papers that you come across that you want to give a shout out to? Folks listening to this can also go and read that paper.
Yeah. This recent paper just won an award at the OOD workshop, out of distribution data workshop RSS. Is by Jesse Zhang at USC. I don't remember the paper name, but you can search up Jesse Zhang. He has
Rewind, right?
He has like a real world language guided RL training system.
Yeah, that's a cool one.
Cool. I've been looking at a lot of real world RL stuff. Another pretty cool project that actually builds on R Simulator also won an award at a workshop, which is quite cool. It's called Rosetta from Stanford.
Oh yeah, cool.
I just saw that they build a digital twin. They do real to sim and sim to real, and they use R Simulator to do a digital twin. Quite cool to see it happen. They do a lot more randomizations than my sim to real demo. Like they literally rotate the camera like 50 degrees. So it was quite cool to see that one and see how they do real to sim. What's like another one that was pretty cool. Yeah, like I think those two were some of the cool ones, like real world RL and real to sim, sim to real were some of the recent ones I've been exploring. They're quite
awesome.
Cool.
Yeah. Thanks. Well, cool. Yeah, this is a lot of fun. It's really cool work that you do on ManiSkill. I'm always impressed. So great. Yeah.
All right. And hopefully you can keep building ManiSkill. I think the community will really benefit from it. Clearly, I mean, there are like very good research paper that's built on top of what you built. So, okay, sounds good. I guess, until the next time. Thanks so much for making the time, Stone.
All right, thank you.
All right, Chris, what have you learned today?
It was really nice going through all the different qualities that ManiSkill had. I really like all the thought. I mentioned this during this, but I really like all the thought that Stone and his team have put into making it easy to use and making it accessible and powerful and easy to do domain randomization. Domain randomization is basically a first-class citizen, it seems like, and like they've really considered how to do this heterogeneous simulation so you can get like really diverse environments, and it's all just like very, very well designed to be like the simulator for robot learning, in my opinion. No, I'm always impressed by the stuff that he's able to show. So I don't know. What did you think?
Yeah, I mean, honestly, I don't know much about simulation at all. Like just a casual observer. So to hear from him was really eye-opening just now. I would say, like for example, what are the dimensions that matters for a simulation, engine like ManiSkill, right? And it's just a bit mind-boggling to me that to do a good simulation platform like ManiSkill, that's so much part of the stack that he needs to know, all the way from physics engine to the rendering, all the way to the the top level, like the API exposure, so that it's things are abstract away, easy to read and code, and it's a non-trivial thing, man. I mean, I'm trying to think like, how do they done it so consistently? This is the third iteration, right? And so to do it is, I think it's an open source it, right? And so I'm really glad that they're doing all this. Yeah, I hope more people can contribute to the project. So hopefully those who listen to this podcast will want to help out. Yeah.
Yeah,
So
I hope
really
it does
cool.
well. Same.
Yeah. All right. Okay. Cool.
Thanks.
I guess until the
See you
next
next
one,
time.
Chris. I'll see you.